Okay, can you see my screen now? I could like to give you some summary of the chapter 23. So you can see that in the chapter 23, we have the definition of electric field. So when you identify the electric force that acts on the so-called test charge Q0 here, then you take the force and divide that by the Q0, you have the electric field at the point where we locate or we put the test charge Q0. So in general, the electric field E can be created by many charges or a charged object in general. Okay, then you have here the Coulomb's law, in which we consider the two charges Q1 and Q0, and we want to find the force that acts from Q1 to Q0, Q2, sorry, according to this equation. Then if you want to calculate the electric field of a single charge Q, then you can use the definition by dividing the force to the charge, then you get this equation, right? To the charge, then you get this if you have equation. A set of charges, then to the you charge, then you get add the E vector of if you have a set of in the set charges, then you get the sum, then you get this as the equation the E vector 23.8 you have a set. But if you have an object in let's say charges, then you get the sum here, or the rod, or the plane, the disc, etc. Then you can use the integral technique, and then you get which you divide the E vector 23.8. You have a object into many small pieces, and each piece have the charge of dq, then you calculate but the if you have the dq over an r object r, like this equation. Okay, this is the theory. Then remember, you can calculate the electric field created by the rod, right? By the very long line, the disc, the ring, and so on. Wait a minute, I have to connect the computer to the screen. Let's say charges, then you get the sum here, or the rod, or the plane, the disc, etc. Then you can use the integral technique, and then you get which you divide the E vector 23. If you have a object into many small pieces, and each piece have the charge of dq, then you calculate but the if you have the dq over an r object r, like this equation. Okay, this is the theory. Then remember, you can calculate the electric field created by the rod, right? By the very long line, the disc, the ring, and so on. Wait a minute, I have to connect the computer to the screen. In the chassis, then you get the gear or the rod or the plane, the disc, etc. Then you can use the integral technique, and then you get which you divide the E vector, 23. Ok, giờ em coi cái này nhé. Can you hear me now? Hello? Now I give you an example for a configuration in which we have many charges like this one. Okay, you see that here I have some charges, positive charges, and they are distributed symmetric along a straight line. Then if I want to know the electric field at some point here, I can put the sensors. Then you see that the computer will draw the vector E vector, right? But you can see that if I put some more charges here, then the electric field will be different. Put the charge here, right? So the electric field at this point can be different, but at this point you can see the direction of the electric field here and there are perpendicular to the segment here, right? You can see that this point is the midpoint of the segment, right? So we can conclude that if you had the segment and you calculate the electric field at the point, and the point is on the line that is perpendicular to the segment here through the midpoint, then E here is perpendicular to the segment. Clear? Now, what happens if I have a very long straight line, very long and straight line? Then, of course, you can use the integral technique to calculate the electric field at the point around the line. But this is very complicated. And we have another tool to do that. This is a Gauss law. So today we will start with the Gauss law. Let's see. If you want to apply the Gauss law, then we have some new definition. For example, first of that, we have the electric flux. Can you see the screen now?
Yes.
Thank you. I enlarged it a little bit. What is the electric flux? The electric flux is the quantity that is calculated from the electric field and the area in the electric field. For example, here, if you have the electric field and the lines of the field is shown in this picture, can you see that? Right? We have here the uniform electric field because all the lines are parallel to each other. They are parallel to each other, right? And if you measure the distance between the two adjacent lines like this one, then you will see the distance between the two adjacent lines are the same, right? Then in this case, the flux is the production of E and A, of E and A. But if you have some angle between the lines and the area as here, you see, we want to calculate the flux through this area. And the normal vector of this area made an angle theta with the electric field lines. So you will have the formula here. I enlarge it a little bit. Right? So the flux E is E multiplied with the E with the area, but we calculate only the area that's perpendicular to the field. Then you multiply the A with the cosine of theta, you get EA cosine theta. So please write down this one, EA cosine theta. Okay, so I can copy the formula here for you. Okay, so you can draw the picture in your notebook and then write down the equation. So this is the case in which we have the uniform. It means you have E is a constant, right? Everywhere in the space, you have the same E vector. But what happened? Sorry, there's another the area. Right? When we have uniform electric field, E is constant, and the area is flat, then you have the flux like this. For example, I give you an example to calculate it. This is a very, very easy example. Please calculate that and tell me what do you get. Okay, 2 minutes is enough for you.